Okay, so we can continue into our next session. So this session is given by DuPont. So as I started with today's conference with my backsheets, and often backsheet topic without mentioning DuPont cannot be completed because the first modules were used using DuPont Stedler as backsheet. But today we have Kaushik Roy Choudhury, Senior Scientist and Project Leader at DuPont Photovoltaic and Advanced Materials. He's going to talk about what's really needed for designing long-term solar panels. And Kaushik is currently leading DuPont's global PV field reliability program, working on reliability, durability of PV packaging materials, degradation of polymeric materials in the field deployed PV modules. And of course, he also works on PV system economics. At DuPont, he has previously led programs on metallization paste for silicon photovoltaics, novel inorganic and hybrid thin film solar absorbers, light emitting plasmonic nanomaterials. As for the education background, Kaushik has a PhD in materials physics and has over 15 years of experience in photovoltaic and optoelectronic materials. Good morning, Kaushik. So Kaushik is really joining from US, so he just probably woke up. Floor is yours.
Yeah. Good morning, good afternoon, good evening to wherever you are. Yeah. Shravan, it's nice to be here. Am I coming in clear?
Yes, I think only you have to share your screen.
I will be. Yeah, I will be. Okay. Let me start. Just give me 1 second. Okay. Please let me know once you start seeing it.
Yeah, we see your screen.
Okay, thank you. Again, thanks everyone. Thanks to TaiyangNews for inviting us to share our perspective on this unique conference dealing with module materials, especially with the focus on module packaging materials. Shravan, thank you for the nice introduction. As Shravan mentioned, I'm the global technical leader in PV reliability within DuPont Photovoltaics and Advanced Materials. And my team works on developing new materials for the PV market, as well as looking into accelerated testing and field information from around the world. So this whole topic that I'll be trying to share my knowledge and information on is very close to our heart, as well as our daily work. Okay, so just a little bit of background to start off with. DuPont has been serving the PV market for well over 30 years now, with pretty much 3 flagship products. There were quite a few other products earlier, but right now with 3 big flagship products: the metallization pastes by the name of Solomet, polymer-based backsheets enabled by the PVF Tedlar material, and then silicone encapsulants under the brand name of Fortisun. Fortunately for us, all of these materials have been in the field, proving their performance and reliability for well over 30 years. And we believe this is a very unique way of driving LCOE lower. And I'll try to share what kind of information and what kind of learnings we have from here, which we take into designing newer materials. So the next chart, I don't really need to go into this, but I always start with this because I guess everyone has this on their minds, be it midstream module makers, material suppliers like us, and definitely downstream asset owners. So there are several aspects of or several buckets that go into the overall calculations of LCOE or return on investment, all the way from module costs, the balance of system costs, efficiencies, energy yields, module durability, as well as system performance and other things. Of late, we have been trying to talk about slightly recasting this in a slightly different light, where we try to think of not just of LCOE, but of an overall total lower cost of ownership. The concept is very similar. And in this case, we generally try to look at material durability, which is actually one of our biggest concerns in the PV area. Obviously, performance and higher energy yield, and then installation costs and manufacturing processes. The interesting thing is that whichever formalism we are talking about, we see module durability and material durability coming up as a prime factor in each of these. And that's what I'll be focusing on mostly for this presentation. So here's just a little bit of a study that we did some time back. Don't pay too much of attention on the exact LCOE numbers. The LCOE numbers vary depending on whether you are in a utility scale project, which part of the world you are, etc. What we are trying to show on the left over here is this work was done on four installations in the US. And what is being shown here is how the overall LCOE gets affected with a certain percentage of module being replaced due to non-performance or failure or defects. And as we can see here, over a range of possible module replacements, the LCOE can significantly vary, over as close to in this particular case, all the way up to 40%. On the right, what we are showing here are two sort of seminal points. One is 1% degradation, nominal degradation that we are used to. Actually, a lot of financial calculations include even a lower percentage degradation. And then what happens if we change it to a higher degradation rate? And what we are doing is we are doing a sensitivity analysis to see how LCOE varies with these two nominal degradations versus some modest module replacement. What we are seeing here is that LCOE is actually much more sensitive to module replacement than to nominal power degradation rates over the lifetime. So again, kind of drives home the importance of materials that actually last and perform over their entire lifetime. Okay, so as I mentioned, part of my group is actually very involved in the field. So we take field data very seriously, and we always look at the field to inform us whenever we are designing new materials for either a new technology or an existing technology. And frankly speaking, field reliability is very important. That's one of the main reasons being increasing field failures can actually threaten the long-term performance of any asset, leave alone the expectation that it would last for 25 to 30 years. Obviously, all of us know that all modules and all materials are not same, and degradation rates are also different, defects are also different. What I'm showing here on the right is a snapshot of defect trends that we are seeing in our annual global field analysis. And this is, by the way, an analysis that DuPont does year over year for several years now. And we have amassed over 3.5 gigawatts. This is a little dated, but I'm using one of those charts that I had, over 3.5 gigawatts. And year over year, what we are seeing is an increase in the number, in the amount of defects in the field. What kind of defects are we seeing? Again, the reason I'm spending a little bit of time right at the outset to drive home the importance of what we are seeing in the field is, as I pointed out, is because we really want to learn from the field holistically from a module, from a materials perspective, from a packaging perspective, and then hone in on maybe one or two of the materials that we produce so that we can meet these requirements or avoid these defects. So in terms of the types of defects which we are seeing in the field, I'm not going to go through these. Everyone is very, very familiar. But the important thing that we are showing here, I'm showing a bar graph over here. And compared to 1 year earlier in 2019, most of the defects that we are seeing here are either increasing or staying within the experimental error of data taking, and they're staying the same. This tells us that the overall defects are actually not going down with time, but can become a significant issue as more and more deployments go on. So for the rest of the talk, I'll actually try to focus a little bit more on the backsheet part because that's what Shravan, as he mentioned, he's expecting me to talk about, and that's one of our areas of expertise. So if we think about backsheets, what are the trends that we are seeing? We see three main things from our 2020 global field analysis. And I'll quickly take you through these. This is one of the very prevalent backsheet material types that's been deployed in huge numbers over the years. What we are seeing is actually kind of a concerning trend. On this bar graph on the top, I'm showing cumulative years in field of panels. And on the left-hand side, on the y-axis, is plotted the overall defects in this particular type of backsheets. Even if you disregard some of these actual numbers, what is concerning is the trend of increasing number of defects as we go through the number of years. As high as over 20% for 9+ years of modules in the field. The map on the right actually drives home the point that this is spread all over the globe in different areas. And here are some examples from different parts of the world that we are seeing. Another reason that this concerns us a little bit is the nature of the defect that we are seeing in this material is very reminiscent of another material that has been known to be defective in the field, polyamide in this case. And if we even look at the trends of the defects between polyamide and PVDF, yes, we always have seen this increasing trend with the number of years, showing that the material degrades more and more as we are going through the number of years. The next type of defects that we are seeing is the inner layer crackings. So the earlier one was the cracking of the outer layer, which is probably one of the most egregious defects that a backsheet could have in the field. In this case, these inner layer cracks actually originate at the inner layer as the name implies, and then they propagate through the polyester core, which typically forms the core layer of a backsheet. We have seen this frequently in polyamide. Some coated backsheets, FEV is a fluorinated coated backsheet, and several PET-based backsheets. Interestingly, this can actually directly impact power. So this shows up and impacts asset owners much early in the life. Here's another example, a few examples of these from different parts of the world, in India, in the US, China, all across. And this bar graph again on the top shows a year-on-year decrease in the power generation on one of these examples. So this could be a significant issue. The last trend that we have seen, and this would play into some of the materials that I'll share later on, is issues with some double glass modules. As I mentioned, we have been doing these surveys for several years now, so we have amassed quite a bit of data. The main issue we have seen in double glass modules are delamination and cracking. So with this example in Southwest USA, over 10 years, this is actually a framed module and not a non-framed module. And then several unframed modules, as well as framed modules of a variety of ages all across the globe. We have seen delamination, typically originating from the edges and then working their way through. And once the delamination starts, it forms a pathway for other things to get in, leading to corrosion and other things. The other issue are cracking. Typically, cracks again originate at scratches or chips on the glass surface, and then they start propagating. So, okay, enough of the background information and enough of edification from the field. What do we do with it? So, in designing a reliable backsheet for the newest trend of bifacial modules, how do we imbibe all of that information into our design and educate ourselves? So we always start with the field, as I am showing here as my first bullet point. And then we, armed with that information that we get from the field, we design new materials with hopefully robust properties. And then finally, we take it through a battery of rigorous accelerated tests to ensure that we simulate field conditions in as good or as close a manner as we can, so that these materials and these products hopefully will last in the field for their expected lifetime. So let me take you through the rest of this. In terms of the field, unfortunately for bifacial technology, we do not have a lot of long-term experience from the field for utility scale projects. However, there are several building integrated projects that actually used the transparent Tedlar based backsheet, its earlier generation, and which have been in the field for several years now. This is an example, one of the examples of those. This is in Netherlands. This is over 20 years now. It's a building integrated installation. And what it showed us was the earlier generation of Tedlar based backsheet was actually holding up pretty well in the field with no obvious defects that are associated with backsheets in general, no yellowing, no delamination, no cracking. And these are still operating in the field. So armed with that information, we improved upon the formulation on the package that goes in the film that enables the newer generation of transparent backsheets. So this is enabled by the clear Tedlar film. I'm showing here a cross section of the backsheet and pointing out that the Tedlar film actually goes on the outer layer of this backsheet structure, and it performs a very important role of protecting all the inner layers in here from the ravages of weather for hopefully 25 to 30 years. I'll take you through some of the properties and what kind of measures we take to ensure that the product is good in our design phase. So obviously, the product needs to meet the CTQs that would be required for a backsheet material in a bifacial application. It needs high transparency. It needs robust mechanical properties. And as I mentioned just a moment ago, it needs to provide excellent UV protection for the not only the PET core, but whatever lies inside. Here are some numbers just from the initial measurements of the material. It's a 25 micron film, very competitive optical transmission versus the incumbent, which is glass in this area. The other thing that I'm showing here is the optical transmission is pretty much flat across the entire spectrum, which is important. And then I'll come back to this, the MD and TD elongation. These refer to the basically the mechanical properties of the film. Once we have the initial properties, then it's time to look for how these properties hold up versus accelerated aging. So I'm showing here quite a bit of data. On the top left over here, we are showing UV protection and UV absorbance as a function of exposure. So what we are seeing is the overall UV protection is pretty stable and stays pretty stable, well over 300 kilowatt hours of xenon exposure. And this is beyond what the backsheet would see over a lifetime of 25 years. So that gives us confidence. The top right over here shows that the material, which is a polymeric material, does not change color appreciably over this period of time. Again, gives us the confidence that the material is not changing that much. The material doesn't get brittle on the top, bottom left over here. That's what we are seeing. And this is just the film, by the way. We are not at the backsheet stage. I'll take you through the film and then over to the backsheet and finally through the module stage to show that how we are tracking the progress of the stability and durability of the material through the different phases of getting it integrated into the module. So anyway, coming back over here, the film itself doesn't get brittle, again, over 350 hours of UV exposure, and it does not lose the light transmittance that I had shown you earlier over this entire exposure period. So this gives us the confidence that the transparent Tedlar film maintains stable optical as well as mechanical properties after really field relevant long-term UV exposure and UV aging. There has been some field-based work. This is again with the older generation of the Tedlar transparent Tedlar film, which translates very well to the newer generation, which is in fact, if anything, a much improved version. So this study was actually not done by us. This was an external institute. It was done in Switzerland, and transparent PET-based films were compared with transparent Tedlar-based films. And what was seen was that the light transmittance in the Tedlar film didn't decrease even after 20 years. However, the PET-based film became brittle just after 10 years of outdoor exposure. So we are always trying to make this connection between indoor accelerated testing and outdoor exposure. So this is a good touch point on that one. Okay, so once we have evaluated the performance of the film, we want to then move on to what happens with the backsheet. So in this case, I'm showing the results from a backsheet made with the new transparent film. On the bottom left over here, we are showing two things. One is the optical or the light transmission with significant hours of xenon exposure. In this case, the backsheet was actually exposed to an even longer exposure, over 400 hours, kilowatt hours. And along with that, we are also showing the color increase, which is also nominal. So any number that's below 3 in this scale of yellowness actually does not register very much on the yellowness scales. So that gives us again the confidence. Comparing with some existing prototypes of other backsheets in the market, we see that the Tedlar-based backsheet, which is down here, maintains a very low color change, well over 300 kilowatt hours per meter square, whereas some of these other competitors actually are having a significant increase in color, indicating that the material, the polymeric material, which is the main component over here, is changing in some way in the composition. This, by the way, is a metal halide exposure versus the xenon exposure, which was shown on the left over here. It's a much more intense exposure in this case, as you can see from these numbers. Okay, once we take a look at the UV durability, then we also look at, in terms of the color and transmission, we also now look at the mechanical properties of the backsheet, both under damp heat conditions as well as under the UVA exposure that I was pointing out. What I'm showing here in these two charts are elongation at break. Again, this is one of the prime properties that is looked at polymeric materials as a measure of their mechanical stability. And this, for anisotropic materials, is also important to be looked at in both directions of the module. So MD refers to the machine direction, and TD refers to the transverse direction of the module, and we are tracking the mechanical properties in both these directions. What we see here is on top, with over 400 kilowatt hours of UV exposure, there's not really much change in these mechanical properties. On the bottom over here, we are showing damp heat exposures of 3,000 hours. Although I have to mention here that if I can go back to the field, we do not see a lot of correlation beyond 1,000 to 1,500 hours of damp heat exposure as an accelerated test. However, we do want to stress it well over the required IEC values, IEC requirements. So we take it all the way out to the 3,000 hours. And again, we don't see any appreciable change in the mechanical properties. So it gives us the confidence in both the MD and the TD direction. The next, this chart is again showing more mechanical properties. As you can imagine, mechanical properties is one of the crucial important properties that we look at. Over here, we are looking at elongation and break, as well as tensile strength, another measure of the mechanical property of the backsheet, under a variety of different tests. So in this case, damp heat 3000, thermal cycling of 600, pressure cooker test of 60 hours, and 360 kilowatt hours of UV. Under all these conditions, what we see here is that the mechanical properties of the backsheets are holding up well above this required internal requirement. This is an internal requirement that we put, which is shown here with this red dotted line. So it's holding up even after these significant hours of these accelerated testing regimes. Okay. And then finally, one of the other things that we definitely do, and we have been proposing this for actually quite a long time, as anyone in the industry in this area knows, we really believe that a true representation of the field is through a sequential accelerated test, and not just single stresses. And we have been pushing this for a long time. So here's one of the similar tests that's offered by PVEL in the US and over the globe. It's a combination of damp heat, cycles of UV and thermal cycle, and humidity freeze, as well as a short UV at the end. And the transparent Tedlar-based backsheet has been taken through this sequential test in mini modules as well as full-size modules, and it has passed this pretty easily. We haven't seen any yellowing, delamination, or cracking, the things that we do look for. Case in point is that this test actually is very effective in catching the issues that I was showing earlier from the field in some materials like polyamide or PVDF. It has been able to rightfully simulate and predict cracking of PVDF and polyamide-based backsheet. I'm showing examples over here. So this again gives us kind of the full level of confidence that even in accelerated testing, sequential accelerated testing, this particular material, which is a rather new entrant in the field, in the bifacial market, should be holding up for its entire lifetime and performing as expected over 25 to 30 years. Another thing that we check is abrasion resistance of the Tedlar-based transparent backsheet. I'm showing here comparisons of the Tedlar-based transparent backsheet with a couple of other similar products in the market. This is a transparent fluorinated coated backsheet, the second bar, and then the third bar is a transparent PET-based backsheet. What we see here is the transmittance loss after this ASTM test, which is actually a rather harsh test of falling sand on these backsheets. So at the conclusion of these falling sand test for the Tedlar-based transparent backsheet, we see a loss of less than 1% versus 3 to 4 times or even more for the other types of backsheets. So this again shows, gives us confidence that there's very little change in light transmittance after this test, and therefore in real life situations in deployment in even dusty and sandy areas, the product should be pretty good in terms of its reliability. And by the way, as I mentioned, the sand abrasion test is a rather harsh test, which is much harsher than what the modules actually see in deployment. On the PID side, I did hear a couple of questions in the earlier session around this. So obviously we had to test the modules. Now we are getting into the module level testing over here, as well as the sequential testing that I had shown in PVEL was also a module level test. What we have seen is, in this case, I'm showing on the left over here, I'm showing this in this bar graph, comparisons of a glass transparent Tedlar backsheet, which is shown in blue bars, versus a glass module of exactly similar build with a similar BOM, but just the backsheet being replaced by a glass. And we are showing the power loss over here on the rear side of a bifacial P-Park module with PoE encapsulant over here. And we are seeing a much lower loss of power on the rear side. We believe that this has to do with the lower amount of both shunting type as well as polarization type of PID that's happening with this in these modules. This work is still ongoing. Another example from a module that was taken through PID testing at PVEL, and this is actually for 96, so actually 192 hours. And we see hardly any loss in power in this particular case with a transparent Tedlar-based backsheet. Again, gives us the confidence that there will be not much PID risk in these module prototypes. I also heard mechanical loading, and I'm pretty sure people will have questions around this as well. So we did check. This is, by the way, a work under progress. But I'm showing here a couple of protocols that we have been taking these modules through, both on the front of dynamic mechanical loading sequence, where we don't do it just by itself. We actually combine it with a healthy UV dosage, followed by the dynamic mechanical cycle, followed by a thermal cycling and humidity freeze cycle. We do the somewhat similar one with the static mechanical load as well. The two graphs over here are showing the power loss, and I'm not sure if you can see this very clearly, that the numbers are a little bit small, but in both these cases, what we are clearly seeing is that between the glass module and the glass backsheet module, there's not much difference in the power loss on the front and back once we take these through this cyclic accelerated sequential mechanical load sequences. So the top one is the front side power loss, and the bottom one is for rear side power loss in these. And what we are seeing, at least so far, and this is again a work in progress, is that both these types of modules are performing very similarly in this case of mechanical loading. Now, we can always argue as the modules get larger and larger, what happens, but that's an interesting discussion. We are seeing some indications, but I don't have the full set of data with larger modules yet to share. For the last part, for the last few minutes, I want to also touch upon some performance improvements. So I intentionally fashioned most of this talk today to talk about the reliability aspect of the module design in terms of packaging materials. But I do want to point out some of the performance improvements in modules using these transparent Tedlar-based backsheets. So first up, here's some results from a study that has been going on in China for over 8 months now, 4 different type of installations. What has been shown is that bifacial modules with transparent Tedlar backsheets in these 4 different field tests, well over 8 months, they are now producing in the range of about 0.9 to maybe 1.8, 1.9% higher energy compared with bifacial dual glass modules. Exactly the same BOM installed in exactly the same location. So it's a pretty good good comparison in this case. The initial indications show that this is because the modules with transparent backsheets probably operate at a slightly lower temperature, anywhere from 1 to 2 degrees Celsius lower than those with glass on the back. And this is probably contributing towards the increased energy generation in this case. So this should be a good performance differentiator, we believe. I wanted to also point out what we believe is another advantage of these transparent polymer-based backsheets in this case, in easier cleaning and higher resistance to the accumulation of dust. So this is actually a work that we conducted with Fraunhofer, and comparison was made between solar glass in a module format versus transparent Tedlar backsheet in a module format. And Fraunhofer has its own test where they evaluate the cleaning efficiency or cleaning efficacy of regular water once we have a surface, a solar surface with dust accumulated on it. And we see that the transparent Tedlar-based backsheet has a slight advantage over solar glass in this case. Results from the field also indicate that quantifying soiling and dust accumulation in the field, as anyone who has worked in this will tell you, is very difficult. But we have seen all indications that with the transparent Tedlar-based backsheet, there is much less obvious dirt accumulation in this. And once the dirt or dust does settle, it's much easier to clean with water because the surface of the Tedlar-based backsheet is actually a fluorinated material, which is naturally a hydrophobic material. So that is a good combination in this case. And this is important because it does ensure long-term light transmittance to stay at the level that we want it, so that the power generation is not affected. Another example of the soiling resistance. This is another China standards test. This is with a pretty egregious amount of dust and dirt in this case, basically. On the top over here, we are showing Tedlar transparent backsheet versus glass before rinsing with water, and then bottom one is after a rinse with water, and the results are pretty self-explanatory in this case, I believe. And then finally, again, this has been talked about. Don't want to spend too much time on this. There is a certain advantage on that we believe that these transparent Tedlar backsheets bring in terms of lowering the overall BOS, balance of systems cost, and installation costs because of their lower weight. And this is important as modules become larger and larger, because this difference in the weight would diverge, would become an even bigger thing. Along with that, there are several other points that could be also made with the newer innovations in glass. As my earlier speaker was pointing out, a lot of the newer designs of glass modules are moving away from the fully tempered versions to semi-tempered or heat strengthened. They come with their own issues of mechanical stability and impact resistance, but not. I don't have information that I have included in here with that. But we believe that this weight difference actually for the downstream will be a pretty good differentiator, is turning out to be a pretty good differentiator, and will keep on being so as the module sizes get bigger. So with that, I hope I have touched upon the important parts that I wanted to share with you. And I hope I have given you the message that in improving efficiency, in introducing newer technologies for the newer generations of modules, if we are diligent in our design aspects, if we learn from what the field tells us, and we incorporate that in both our materials design, our product design, as well as our testing of the reliability of the materials, then we believe we can actually check off all of these buckets in terms of higher performance, lowering some of the cost, as well as ensuring material reliability over 25 to 30 years, all of which we believe actually are contributing towards lowering the overall total cost of ownership. So thank you. Thank you for your attention. And Shravan, I'm ready for the question and answer section.
Thank you. Thank you very much, Kaushik, for this wonderful insight. You really talked about a lot of technology testing procedures. So, probably our participants would also like to see some commercial aspects, especially now the bifacial glass transparent modules are getting into the mainstream. Can you talk about, like, of course we know Jinko and Jollywood are the two companies, but how it is going on to the commercialization side, from Tedlar side as well as from the transparent backsheet side?
Sure. Yeah, I can probably speak more towards the Tedlar part of it because I'm not privy to a lot of the competitive material that are in the market. But in terms of our own work with be it laminators all the way through to module makers, which is the next step in the value chain. We have now expanded quite a bit, and there are several laminators who are offering the transparent Tedlar-based backsheets. Yes, Jollywood was the first one to be offering it, but we now have several others, Lucky, some others as well. Actually, it's readily available in information that have already qualified the transparent Tedlar-based backsheet and is offering it in their mix. In terms of module makers, there are also several who are actually 3 of them who have actually qualified it, and several others who are in qualification currently. So we are positive, and we have seen, as you know, Shravan, we have talked about this several times. We have seen a rather sharp uptick of the product in the recent months, despite the initial slowdown with the COVID situation.
Okay. So, then I'm also very much, kind of surprised the way you were able to convince one of the leading, actually the largest module manufacturer, Jinko, to provide 30 years warranty with your transparent backsheet. So can you just say a little bit, so what really went to convince a company like Jinko? Of course, they were using your standard opaque Tedlar, but really to go beyond what only glass was able to offer at the time, to convince Jinko to offer 30 years.
Sure, it's not very difficult. I think it all comes down to data. In our case, as you have seen, probably when I was putting together my presentation, I was also thinking whether it's becoming very heavily loaded. But I didn't want to hold back on the amount of data, because that's something that we believe drives our excellence, drives our innovation pipeline, and drives and sets us apart from our competition. So what do I mean when I say data? So a couple of things. One, we have behind us the history of 35, right now actually it's 40 plus years of field performance. So that's actually a big thing. That's actually, I think, an unprecedented qualification that no other material, polymeric material, can claim. So we have modules out in the field which have performed over 40 years. Essentially, the polymeric material, the Tedlar PVF material that goes into the transparent backsheet is essentially the same as it is in the white backsheet. So that gives us the confidence that the polymer itself is the same. So it wouldn't degrade in any unforeseen way in the field. So that's part one, that we have the field part of the information there. The second part, as hopefully I have kind of tried to demonstrate in my several slides, we really take the material all the way from the film to the integrated backsheet to the module level. We really take it through a rigorous battery of tests. We believe that which are more rigorous than any other tests that exist on the market. That again gives us all the way from, say, UV, damp heat, combination of sequences, thermal cycling, humidity freeze, mechanical load, as I've shown, electrical measurements in PID and other things. So we kind of try to cover the entire gamut. It does take us time, and we are often accused of being slow in that sense, especially my team, because I lead the overall reliability efforts. But we want to make sure that we put it out. Jinko is a partner that has believed in this overall balance of reliability with performance for a long time now. So for them to see once all this data was put together, and from independent sources as well, for example, like from PVEL, it was easy for them to see that the extension of the warranty was well in line with whatever testing that was being done similarly in glass or other incumbents. And in fact, in a lot of cases, we are going well beyond that if we think about that. So those are the main reasons, I think.
Mm-hmm. Okay, I think I know your answer, but just for our audience again, so transparent backsheet. Okay, I think I forgot the question. Maybe meanwhile there was a question from the participants. So what is the difference between the old and new generation transparent Tedlar film?
Sure. Yeah. So as I had shown, that there is a version of the earlier generation of transparent Tedlar films that are still running in the field, as I showed from one of those examples. We have several other examples. Not bifacial, because bifacial was not there 20 years back. These are monofacial, but building integrated monofacial mostly. But they are running as well as anything else without any obvious signs of issues. What we have done in this newer generation of the transparent Tedlar film is that we have improved some of the UV packaging as well as some of the mechanical strengthening properties of the film. So we have the overall additive package in terms of UV blockers has been improved significantly, which we believe will extend the lifetime even further and will make it compatible with, because the other thing, Shravan, that's also interesting and important over here is that our Tedlar film actually has to work with a couple or 3 or 4 other materials, even in the backsheet construction. It's not just the Tedlar film, but changes in the PET core, in the inner layer, in the adhesives that have happened, say, since the earlier generation of Tedlar versus where it's now newer backsheets. So it had to be made compatible with these other layers that go in the backsheet, and also enable maybe slightly less expensive materials in that backsheet. So we had to improve our part of the game as the the outer layer protecting material. So we had to improve the overall UV package in there, which we believe will take it out well over 25 to 30 years now.
Okay. So there is also one question from the participant. So I just read out the question. So how much based on NRL failure / degradation has to do with the backsheet failures? Then hotspot leads the way with the most severity, right? So just
absolutely. Yeah, no, fair enough question. So and this is actually an interesting question. I actually want to take maybe a minute to answer this. Sure. With the typical power degradation information and detailed work that NREL has been putting out for years now, that's heavily focused on typically power degradation. One interesting aspect that we have seen is absolutely hotspots lead the way over there, followed by some corrosion, and backsheets probably come in around, I don't know, maybe fourth or fifth in the list over there. Interestingly, from doing a lot of field based work, which is kind of unusual for a material supplier like DuPont, what we have seen is the backsheet defects generally take a few years to show up in the field. As all of us know, backsheets the polymeric material needs to degrade and change over time. And for the first few years, it does not really directly correlate with power loss. So asset owners, asset managers do not really feel the pinch over there necessarily. There are exceptions. The inner layer cracking that I showed sometimes can actually lead to very significant power losses within the first 4 or 5 years. That becomes very visible. Whenever you have a power loss, whenever you're losing money as an asset owner, it catches your attention. But in general, for all the other types of backsheet defects, it takes a few years. However, in my opinion, that actually makes it a little bit more tricky to nail down, because when this actually does catch your attention in terms of, say, either a crack or a delamination or significant yellowing, at that point, it becomes a little bit too late, because now it is definitely a safety issue if it's cracking. However, in a lot of cases, within a couple of years, it also becomes a performance issue. And since it sets in a little bit later, you are probably now much closer to the 10-year workmanship warranty that once you are beyond that time, then as an asset owner, it is much more difficult to replace some of these module components. So that's why it's a little bit more tricky in the sense that it doesn't show up in power loss early on, but once it does, it's a little bit more catastrophic. And just the fact that it's closer to the 10-year mark makes it trickier.
So there is also another question. The question is, most of the backsheet failures are also related to the encapsulant. So with the introduction of a new encapsulant like POE and other TPO related encapsulant, so is it possible that the all failures may vanish? And is there any relevant field study that also includes the latest generation of encapsulations?
Sure. Yeah, good question. I wish. I wish. So first up, I'd like to dispel a little bit of the notion that all of the backsheet related defects are connected to encapsulant defects as well. That's not the case. So encapsulants on their own also degrade. As we can imagine, these are also polymeric materials. They degrade under UV, they degrade under heat, they degrade under, and that degradation is sometimes catalyzed by the presence of moisture. However, and in some cases, they do degrade in combination with the inner layer of the backsheet or other components. Encapsulants have also come a long way. For example, the typical ethyl vinyl acetate based encapsulants, EVA polymer based encapsulants, they have come a long way in terms of improving their volume resistivity to reduce PID, in terms of reducing the content of vinyl acetates to reduce yellowing and other degradation. With polyolefin based backsheets, what we have seen is the concern that I have is EVA is a slightly better understood beast in the sense that it has been in the field for longer. There has been a lot of deployment of EVA in the field. Polyolefin-based backsheets, polyolefin-based encapsulants have not been in the field for that long. And they have their own degradation mechanisms. There was one belief that POE does not yellow in the field after a few years. It does yellow. The other interesting thing is POE is is being used very heavily in bifacial, especially in dual glass as well as with glass and polymer-based backsheets. Um, Interface adhesion properties of POE with glass is an interesting area of study, and actually several Department of Energy projects as well as other projects are coming up trying to look at this in the United States because it's a less understood area. So there are examples or indications that it could turn out to be another issue leading to delamination of the glass from that. So it remains, I would reserve my judgment at this point to say that, okay, once we move to POE, everything will be solved because it needs to be in the field for a little bit. And we have seen some indications that, again, not all POE are created the same. POE is a very broad class of materials. And depending on the stabilizers, the actual polymer that's being used in there, sometimes a mixture of polymers are used. You can end up not where you want to be.
So probably the last question. So how important it is to balance the technological advancements, with reliable module materials?
Yeah. Again, we live this question every day at least in our work.
Yeah.
I think it's of paramount importance. I cannot emphasize enough the importance of balancing out the technological advances, which are, I used to think that the PV industry was a rather slow-moving industry. If you look at the adoption of the time it took to adopt PPERC on this kind of a scale versus what was there before, it took several years. But over the last few years, there has been a lot of changes that are being introduced both at the cell level, at the module packaging level, at the construction level, all the way from half-cut cells to multi-bus bars to closer spaced cells, larger modules, frameless, frame, thinner glass, a lot of different things. Again, my personal belief is that we really need to balance out this real fast development with some reality check in terms of better testing, more rigorous testing, more realistic testing, because all we are trying to do with accelerated testing is somewhat trying to look into the crystal ball. Weathering science is very difficult to predict. It depends on areas, it depends on local climates, it depends on a lot of different things. And we are trying to predict that in 2 months, 3 months, 4 months, maybe at most 6 months, what we are expecting out of these modules and these materials for 25 to 30 years. And the banks and the financial institutions are betting their money on that. So I cannot stress enough the importance of needing that balance between technology push, which definitely drives the market, trying to balance it out with a realistic check on how these materials would perform for 25 to 30 years, or even longer. Now, some of the financial models are actually putting in 35 years in their calculation. So as an asset owner, as a service to the asset owner, I think different parts of the value chain, all the way from material suppliers to module makers, to independent energy farms, to test labs, we really should emphasize the testing of these and to ensure their reliability over the long term.
Okay, thank you very much, Kaushik. It was really very wonderful to talk to you again. We've been talking several times, but on a public platform, I think this is very nice. Thank you very much for your deep insight, and we learned a lot about reliability.
Thank you. Thanks for this opportunity. It's always a pleasure to talk with you. We talk several times every year, but this was thanks for the opportunity to present my work, and I'd be open to any further questions, queries from anyone who's presenting today or attending today. So I look forward to the rest of the session. Thank you.
Okay, thank you. Enjoy the session.
Sure.